So you know Dirac notation now in terms of its connection to linear algebra and states of qubits. The first example you saw was writing a qubit state as a linear combination of the computational basis, as we called it. This is a ket, and the ket represents a vector in a complex two-dimensional space. The bra was the complex conjugate transpose of the ket and could be written in this way. And we combine these things to get real numbers. The calculations that we do in quantum mechanics are inner products. So we multiply that bra times the ket to get the bracket. And just to make the connection back to linear algebra, we'll do this as matrix multiplication. But in the end, we want to see how everything that you know in matrix and vector linear algebra can be written all in terms of these bras and kets in Dirac notation. So recall that we can find out when we multiply things together what we'll end up with, the size of the thing we'll end up with through this dimension analysis. If I have a 1 by 2 and then a 2 by 1, those inner dimensions have to line up. So in this case, there's a 2 in the second dimension of the row vector and a 2 in the first dimension of the column vector. So they line up. That's good. And those two will contract and produce just a, well, in this case, a 1 by 1, which is just a one-dimensional complex number. This complex number you can calculate quite easily. Basic matrix multiplication, and this is the magnitude of the first complex number plus the second, and that's sometimes called the norm or the modulus or the magnitude of the vector, and for quantum states that has to be 1. Now we could have multiplied these objects in the opposite way, so instead of the bra ket we could have ket bra, and I've written them down side by side here. Sometimes when we're doing these calculations quickly, things can get a bit messy, so you'll see instead of me writing them separately, I'm going to write them in a different way. So let me erase that and write, so I've drawn a big X there. That's just the two angle brackets meeting together. It makes it faster to write, and I think it looks a lot better. Perfectly lined up brackets. So we have alpha, beta, and then the complex conjugate now on the right hand side, alpha star, beta star. If we do our dimension analysis again, we have 2 by 1 this time, 1 by 2. The inner dimensions line up, so we can contract these two things and end up with 2 by 2. That's a matrix. What does that matrix look like? It looks like alpha, alpha star, alpha, beta star, beta, alpha star, and then beta, beta star. Now we could have performed this calculation entirely in Dirac notation, so let's do that and see what we end up with. So the first one is the ket, which is the original state we started with, alpha 0 plus beta 1, and then we multiply that by the bra, which is the complex conjugate, alpha star 0, bra, beta star, and bra. Now we have a binomial expansion here, so we're going to end up with 4 terms. First one is alpha, alpha star, and then we have this ket bra 0, 0, and then alpha, beta star. So now we got this term here, alpha beta star, 0, 1. Now we're going to look at the beta term that's in the first one. So we'll have beta alpha star times those two Dirac notation objects, the cat and the bra. Beta alpha star, 1, 0, and then the final term, beta star, 1, 1. Okay, so notice that we have all of the same coefficients here, and if we had done the calculation of each of these things individually, we would see that everything lines up. So that object there, the ket bra of the 1, 0, 0 object, is one with the 1 in the upper right entry. The next one has a 1 in the upper left entry. The next one has a 1 in the upper right entry, and so on. So we have 1 in the lower right, lower left, and then finally 1 in the lower right. Okay, so and that makes sense, because when I multiply this coefficient alpha alpha star times this matrix here, I'm going to get that element up there. Okay. So we have 2 different ways to multiply these bras and kets together. We have the inner product. So that's when I take a bra and then a ket, and I produce a complex number. And this other one is given the name unimaginatively, the outer product, and that's when I do the opposite. And a very special outer product is when the 2 labels are the same, as we saw above there, and that's called a projector. And so that's when we have an outer product where the labels are the same. And the reason it's called the projector is if I apply this to some matrix, some vector. So remember that this outer product is a matrix, 2x2 matrix, so then I can multiply that by a 2x1 column vector, so a ket, and that combines to produce the inner product between psi and phi. So that's a complex number that can come out in front, and I end up with the inner product between psi and phi times this vector, this ket. So this original object, this outer product, took any vector whatsoever and produced psi times some scaling factor. So that's like when we look at the projection of a real vector onto one of the cardinal axes. It's something that we can just say draw a picture. So if I have in the usual Cartesian plane, if I have a vector and I say what is the projection of that vector onto some axis, I end up with this new vector, which is in the x direction but scaled by some amount. So that's what a projector does. Those aren't the only matrices. In fact, I can write every matrix, because you can see that these 4 objects here form a basis now for the space of 2x2 matrices, meaning any matrix whatsoever can be written as a linear combination of these 4 objects. So we can look at some examples. So let's take the identity, and you'll recall that that has 1s on the diagonal, and so I can look at these 4 matrices and say that the identity is this one plus this one, which is this outer product times the set of products. So that is 0, 0 plus 1, 1. And remember, I didn't have to go through this step of looking at the matrix. So from now on, we can just write the identity as this particular linear combination here. We also looked at the X gate, the logical NOT gate, and that one has the other two outer products that we didn't consider the identity. So that's 0, 1 plus 1, 0. And every, as I said, every 2 by 2 matrix will be some linear combination of these 4 outer products. Now, the nice thing about having this way to write the identity matrix in terms of Dirac notation is we can start to play some tricks. So multiplying any object, whether it's a vector or another matrix, by the identity doesn't change it. So if I have vector psi, I can multiply it by the identity, and that doesn't change psi, because the identity takes any vector or any matrix to itself. However, I can, because this hasn't been changed and the identity is equal to this sum of outer products, I can just plug that in and see what happens. So I have this binomial times this vector psi, that vector distributes inside of this bracket, and I end up with what we saw before. And we see that we have a complex number here and a complex number here, so we can write that as 0 psi times 0 plus this other complex number 1 psi times 1. And we've now written psi completely in terms of these abstract vectors. So remember, before we had to give these things names. They were alpha and beta, and alpha and beta are implicit here. If I tell you psi, you don't know that I've labeled the coefficients in the computational basis alpha and beta. But with Dirac notation, there's no ambiguity whatsoever. So any vector, two-dimensional column vector, can be written like this, and there's no reference to new variables for those entries. So psi on the left and psi on the right. That's quite nice. We can do the same thing with matrices. So if I have a matrix A, I could have written it out in terms of its matrix elements, and it didn't really matter how I labeled those. A sensible one might be, let's say A00, A01, A10, A11. So just labels for these arbitrary elements of this matrix. But we can play the same trick. Since the identity doesn't change anything, I can multiply by the identity from the left and from the right. So that's going to look like a little bit longer of an expression, but still manageable. So we have 0 and 1. Okay. Now, again, we only have 4 terms to consider. So the A is kind of being sandwiched between the binomial that we considered, these binomial expansions that we considered before. So we can look at the first term which would be this times A times that. The second term is going to be this times A times that, and so on. So A is going to come with every single term in this binomial expansion. So let's do that calculation. Those are the first two terms, and we'll use a second line here for the term where we have 1, A, 0, and then there will be only one term left. So 1, 1, A, 0, 0, plus 1, 1, A, 1, 1. And again, we have some inner products here. Those are just complex numbers. So this is an inner product. It's just a complex number, which means that can come outside. And similarly for the other three terms, there's a complex number there. So let's rewrite this where those complex numbers are in front of the outer products. So we have 0, 0, 0, A, 1, 0, 1, plus 1, A, 0, 0, 1, plus 1, A, 1, and 1. Okay, so that's how you write. Remember, we can write any matrix whatsoever as a linear combination of these four outer products, which form our basis for matrices. And now we don't need to make reference to some new labeling for those coefficients. They're all written in terms of the original matrix. If I wanted to write that out explicitly as a matrix, I can just put everything back together. Remember, the 0, 0 outer product is just the matrix with a 1 in the upper left, so I end up with the inner product of 0 and 0 with the A being applied to the ket inside. And we have the 0, 1, the 1, 0, and finally the 1, 1. There you go. So this is the way that you use Dirac notation to do everything that you can possibly want to do in 2-bit linear algebra, 2-bit calculations, all within that formalism. So you'll need this in your future assignments and quizzes. Good luck.